So take this example. This is a perfect example for flip the bottoms theorem because the bottom is in fact a fraction. And so if this is given, I can say, you know what, this is 7 times 7 over 5 by flip the bottoms theorem. That's got all these steps built into there, the flip the bottoms theorem. And so I can say, well, this becomes 7 over 1 times 7 over 5. This is by out, and then I can multiply across, give me 49 over 5. Multiply across theorem in some times tables. That's how you use the flip the bottoms theorem. Anytime you have a fraction on the bottom, just flip it. You can even do it when the bottom doesn't appear to be a fraction, although here we could also bring it down as using definition of a to b. If the bottom is not a fraction, you could make it. So this is 3 over 5, all over 5 over 1. This is by the out theorem. And then you can flip the bottoms, because now the bottom looks like a fraction. Flip the bottoms theorem, and then take it from there, multiply across 3 over 25. Multiply across theorem. Of course, you could also get from this step to that step just using definition of a over b. Alright, that wasn't so bad. Let's try another example. This one we already did. Alright, let's try this one. So again, this is given. So we say, okay, this is 12 over 5 times 7 over 5. Why? By flip the bottoms theorem. I took the bottom and I flipped it. And so then that becomes just 7 times 12, which is 84, over 5 times 5. This is math. And just do a little times table. 84, 25. There you go. Nice, huh? Flip the bottoms. Alright, let's do this one. This one you can't really flip the bottom because the bottom is not a fraction. In order to apply that, you got to have the bottom is a fraction. In this case, it's not a fraction. It's a difference of a couple numbers. So we could fix that. We could make both of them as fractions. As a matter of fact, this is 12 over 5 plus this is 5 over 5 on the top. This is by just one theorem. And you could think about where we're going. I'm going to try to add these two together into one fraction and add these together into one fraction. That way it turns it into like one of these problems where you just have one fraction over one fraction. So the bottom would be, of course, 3 times 7 is 21. 21 over 7 plus negative 5 over 7. I'll just BI that. That means by inspection. That means these are steps we're very, very familiar with. Alright, so I have same denominator, same denominator. This gives me, I can just add the top. This gives me 17 over 5 on the top. On the bottom, that gives me 16 over 7. Again, this is by inspection and ATT. And now look what we've done. I've combined these into one fraction on the top and one fraction on the bottom. And now I can use the flip the bottoms theorem. So it would be 17 over 5 times 7 over 16 by flip the bottoms theorem. And now I just multiply across. So this will give me 17 times 7 all over 5 times 16 by multiply across theorem. And I'll let you finish that using the times table. Alright. The lesson here is that even if they're not one fraction, you can't go on doing flip the bottoms, but you could combine them into one. And there's actually another way to do this, and maybe we should do it in a different way just for fun. Just so that you become fluent with all these ideas and you become comfortable and you're not just like a one-trick pony. You don't want to be a one-trick pony, do you? By the way, these complex fractions are fascinating. This is only the beginning of the story. They can actually go on forever and ever. I'll talk more about that in a little bit. Anyways, let's do this in a different way, just for fun. So in this case, I try to focus on the denominators, and I think to myself, you know what, I don't like these denominators. I don't like the 5. My life would be better if the 5 wasn't there. My life would be better if that 7 wasn't there. Or not, maybe, I don't know. But suppose you didn't want these. You try to focus on that angle of the problem, and you say, you know what, what would cure a 5 on the bottom? By the way, I don't like these minuses, so I'll make it a... I'll use definition of subtraction, and I'll negative wherever you want theorem, and I'll put the negative up there. But the thing is, I can always multiply by 1 here, and so I did a bunch of little things, and I did multiplicative identity. Here, by a bunch of little things, it means definition of subtraction, and negative wherever you want. And the trick here is to write it as 12 over 5, well, times 1, or no, plus 1, all over 3 plus negative 5 over 7. And I'm going to change that 1 into a 5 times 7 over 5 times 7. or 35 if you want to be a pattern hider. And why? Because that 35 will kill the 5 and it will kill the 7. Watch next, I multiply across, so that becomes 12 over 5 times, or plus 1 times 5 times 7 all over 3 plus negative 5 times 7, 5 over 7, times 5 times 7. This is by multiplying across theorem. And then I distribute this, so this becomes 12 over 5 times 5 times 7. And that becomes plus 1 times 5 times 7. I take this and I distribute it to that, and I distribute it to that, of course using the distributive law. And then on the bottom here, I'm going to take that and distribute it to that and to that, to each of the terms. So this will become 3 times 5 times 7 plus negative 5 over 7 times 5 times 7. Again, by distributive law on both the top and the bottom. And watch how nice that turns out to be. What that does effectively is kill all the denominators, because that 5 will cancel that 5, and I'll let you think about the steps why. And this will just become 12 times 7. This will just become that plus that, and on the bottom this will become 3, or I could say 15 times 7 plus the 7 will cancel that one, and all you get is negative 25. And of course this is by inspection using ideas from previous chapters. And now look what you have. You just have a plain fraction with no fractions on top or fractions on the bottom. Just plain numbers on the top and plain numbers on the bottom. So we can just add them. That's 100, 115, that's 119. And on the bottom you have 70. 70 and 35 is 105. 105 minus 25, that's 80. And so now you clean up the fraction in a different way. And that the idea there was multiply top and bottom by the LCM on the denominators. Multiplying top and bottom by 5s would kill that 5. Multiplying top and bottom by 7 would kill that 7. Give us a really nice expression with no fractions. This is another way of doing it. So we have two ways of doing it, at least. We kill the denominators, that's this way, using the LCM. The other way was combine the fractions on the top and combine the fractions on the bottom, so that you just have one fraction like this, and then use the flip the bottoms theorem. Either way, whatever you like is better. Whatever you like is good. Let's try it one more time just for fun. I got a 5 and a 3, 25 and a 21. I got 5, I got a 3, I got a 5 and a 5, I got a 7 and a 3. So the LCM would be, I need a 5. I'm doing this kind of stuff right now where you try to find the LCM for all these. I need 2 5s. That takes care of these ones. I need a 3 and I need a 7. That's the LCM. So what I should do is I can multiply this by 1 using multiplicative identity, and then I'm going to change that 1 again. I don't like this minus, so I'm going to change that 1 into a 5 times 5 times 3 times 7 all over 5 times 5 times 3 times 7, and this is by just one theorem. And then I'm going to multiply across and distribute it. So this will become 12 over 5 times 5 times 5 times 3 times 7 plus 2 over 3 times 5 times 5 times 3 times 7 all over, that's this one being distributed to that and being distributed to that. Now on the bottom I need to do the same. I got 7 over 5 times 5 times 5 times 5 times 3 times 7 plus negative 5 over 3 times 7 times 5 times 5 times 3 times 7. That's by math and distributive law. Again, I glue the two fractions together. This is a whole fraction here. I glue the two fractions together, and then I distributed that to that and that to that using the distributive law. Distributed that to that and that to that, and that's what they gave me. Now it looks crazy, but it cleans up extremely nicely. These 5s would cancel, the 3 would cancel with that one, the 5 would cancel there, the 5 would cancel there, the 3 would cancel there, the 7 would cancel there. And the point is that all the fractions will be cancelled. Now I'm left with something like this. 12 times 5 times 3 times 7 plus 2 times 5 times 5 times 7 all over 7 times 3 times 7 plus negative 5 times 5 times 5. And that's by inspection, and now it becomes really a much easier problem because there are no more fractions. I would probably use a calculator here to multiply this out and multiply that out and then add them. And the same thing here, multiply that out, and add this plus a negative that, and then you'd be done. I'll let you finish the rest of that. Complex fractions, they're not complicated, they should be called fun fractions. Many ways of doing it. Again, this method focuses on killing the denominators. The other way to do it is you go to get a common denominator on the top, add those, get a common denominator on the bottom, add these, and then flip the bottom. That would be another option. Alright, just for fun, you should maybe, after you pause the video or after you finish watching it, try a fraction like this. This one has a little extra fun because it's 1 plus 1 over a fraction, which is plus 1 over another fraction plus 1 over another fraction. So it's really a fraction of fractions of fractions of fractions. It's kind of a major topic actually, and it might be fun for you to try something like this. I mean, people have written books about this. Look at this book right here. Continued fractions is a fancy name for that kind of stuff. You have things like pi, the famous ratio of the diameter to the circumference of a circle, pi 3.14, can actually be written as a fraction like this. But of course it goes on forever and ever and ever and ever. Entire books about this stuff. Look at that, a bunch of complex fractions everywhere. Whoa, look at that. Does that look fun or not? You can't have my book. Alright, we'll see you guys here next time. Peace.